5, we are going to cover things about the temporal dynamics of this process. And this is a really important part of this issue, that when we talk about response, we are talking about the temporal dynamics. So we are talking about something that is happening over time, and how, if we have a stimuli here, how long does it take to start the response? How steep would be the response? How long we have a response here, and how people would come back. And it probably, we can change the color. So you can see that there are people who are responding later. They can go lower, but they can go there. They can come back soon. So you can see people have different, let's say, latency, different levels of height for different emotions, and different kind of resolution. So they would just go down in a kind of a faster or kind of lower response. So you can have people have, let's say, I usually call it as something like an emotional profile. So people have different emotional response profile, that they can have different levels of kind of variation in temporal dynamics. But eventually we know that there is a temporal dynamics. So considering temporal dynamics is going to be an important process. I told you before that when we have emotional stimuli coming inside the brain, there is a pathway to have specific levels of information towards amygdala and orbitofrontal cortex. So they can receive information even sooner than some secondary visual processing areas. So we know that our amygdala would be informed about threatful stimuli outside in just less than 100 milliseconds. So they receive information far faster than the other areas. Then we will have processing in the visual areas, and then from visual areas the data would go to secondary visual areas, and then from secondary visual areas data would go to these parts again as well. So that would go to something like 100 to 200 milliseconds afterwards. And then after that we have activations in body that would be represented in the insular cortex in the interoception process. And then these kind of responses would make the meaning of emotion for us. So without having those bodily sensations and physiological changes in the body, it is hard to understand the type of emotion that we are experiencing. So there are people who think that whatever we are labeling as emotion would be a kind of re-experiencing what is happening in our body, and real kind of naming that as different sort of emotion. So without having those somatic parts of the emotion, it's really hard to have a full-blown experience of emotion. So we know that these parts would get involved pretty slower compared to the other parts. So we know that there is a temporal dynamics in this process. And it's also important to consider this temporal dynamics when we want to understand the neurocircuit parts of the brain activation. In a study, we have recruited people with heroin dependence, and we have done a drug cue reactivity among them. And of course, we had activations in amygdala. These are the activations you can see in amygdala. And we also had activations in their DLPFC areas because of course, they are in abstinence-based treatment. So their brain, their kind of deep parts of their brain, these parts are involved, are still responsive to the cues, but they also have top-down control with their DLPFC areas, trying to control emotions that are related to seeing drug-related cues. So both of these systems are working, but When we just have activations, we cannot really say anything about how they are interacting with each other. So we have done a study on that, exploring that with the method that we call dynamic causal modeling. And we realized that this is the DLPFC, this is VMPFC, these are amygdala, okay? And these are the visual input to amygdala. As you can see here, obviously there is a significant relationship between VMPFC and amygdala, and there is a top-down regulation from DLPFC to the interaction between VMPFC and amygdala. So VMPFC is connected to amygdala, and DLPFC is exerting its top-down regulation over the link between the VMPFC and amygdala. This is the model that we found within the interaction of these areas. So this gives you another level of it. This is not just the activation. These areas are connected to each other, and this is the way of connection. Ventral medial prefrontal cortex is connected to amygdala, and the LPFC is exerting control over this connection. This is the model that we found with running what we call dynamic causal modeling of connectivity analysis. Okay, and then the question was, okay, how is the temporal dynamics of this connection? Do we have any changes in the temporal dynamics of these connections when we go from the first exposure to the drug cues towards the last exposure? Do we have any temporal dynamic changes over time when we see the first picture to third picture, the 20th picture? So when we go through the time, do we have any changes in the temporal dynamics of this connection? This is the temporal dynamic response. You can see that the input from the visual side is just going higher, and then top-down regulation is just going down. And that is what we have in terms of a level of fatigue in top-down regulation to this connection. So having the temporal dynamics of these responses would give us another level of understanding about how this system is working and give us a better sense about how this neural mechanism is functioning. In another study, in a totally different database, in a totally different project, we have explored some other temporal dynamic responses. And obviously, as you can see here, this is another totally different setting. We showed that right amygdala is responding, but the response is just habituating over time. But we had response in left amygdala, but the left amygdala response was something like this. It was pretty much stable. So there was higher reaction for drug compared to neutral, but the left one was stable and the right one was habituating. So, and there are other studies in this direction as well, that it seems that right amygdala and left amygdala are quite different in terms of the response to the cues, and so to even emotional cues, different sort of positive or negative emotional cues. And one of them is more dynamically responding, and the other is more statically and sustainably, or in a sustained mode, respond to the external stimuli. So they can behave totally differently. You might ask me, have you explored to divide your amygdala in 2 pieces or 4 pieces to see how different nuclei within amygdala are responding? No, we haven't done that. But that is something that you can do and people can do in the future in terms of even exploring how different parts of amygdala are responding to that. One last piece in this section is another interesting finding in the same way in terms of left amygdala and right amygdala. In the study, people realized that in men, as you can see here, left amygdala is less responsive to emotional stimuli compared to right, and in women the process will be totally different. So in women we have mainly left amygdala activation, and in male we had right amygdala activation. So that could give us a sense about how these sort of brain processes could be even affected by gender. and how gender could make a level of difference in terms of how we respond to different stimuli. So people are still exploring these, let's say, gender basis of emotional responses. And I was just interested to add that to the temporal dynamics that we have been discussing about how men and women are responding in terms of the temporal dynamics of their amygdala. So there are still many questions in terms of, okay, how amygdala are responding in different gender, and how amygdala are responding in a sustained way or in a habituating way, or sometimes even it would just get more sensitized, and how other parts of the brain are interacting with amygdala in this process.